So we have a problem. So we use foot placement strategies to estimate where to step and to make stable walking. And usually, so this can be done by a capital point or extrapolated center of mass. Usually we use a very simple model to estimate in such positions. But when we apply these positions to the high dimension robots, then we have a problem as to how do we get there. So we have more joints and we need to specify the gait patterns. And many solutions are given, so we can use position control, and so we define a very exact joint reference for every joint, and we drive the legs there. And also, for these strategies, we have very stiff joints, and which is not adaptive to the changing of the environment. And then we can have use a soft method to have a lower impedance control, such as virtual motor control. And for such a method, we consider the local dynamics, and we try to push the legs, and we put spring here. But sometimes when we want to go to a really complex motions, we need really to coordinate all the body dynamics. So we have to consider of the whole body dynamics. So is there a solution that provide our such functions like no predefined trajectories, tolerance of perturbation, and also consider of fluid dynamics? So what we provide is, as many groups already have this, is the model predictive control. So what we do is using the model predictive control to calculate the desired gait patterns, and also calculate the desired torques to make this robot working. How does it work? We have 3 steps. First, we define a control objective. So usually these are the end positions. So if you want to make step, then you specify the end position of the foot. And if you want to sit, then you specify the end posture of the robot. And then we use a forward model to simulate all the possible solutions. And then we can form some errors between the current position and the future position to the end positions. And then we solve an optimal problem by adding some constraints such as maximum torque constraint, and also add some nonlinear constraints such as foot height, and so that we can avoid obstacles. Then we solve this problem, we apply the desired torques to the robots and finish such a loop. So what is important in it is to define the state machine of the walking. So we have different scenarios, and such as sitting, stance, and walking, so changing in the different phases. So usually for a still phase, as sitting and stance, we control the position of the center of mass. And then for the dynamic, for the walking, we will control the speed of the center of mass. So in the double stand phase, we inject or decrease the energy to accelerate or decelerate. And for the swing phase, we control the foot placement and also control the strictly timing to where to step. And then for such model-based method, a very important thing is the accuracy of the model. So to test such robustness of our method, we introduce the human in the loop. So what we do is, so for the robot is no longer take charge of its trunk. We use human, so we sense the human trunk motion by a Kinect and map it to the robot, and let the human to control the trunk of the robot, and for the controller to control the lower part, which means the lower part, the controller doesn't know that the viscous muscle is controlling the trunk. The meaning of doing so is that it looks like a Segway, but we have legs, so we can call it legway. So then further on, we can build exoskeleton for the lower limb disabled patients. so who cannot walk, but they can use their trunk. And when they wear such exoskeleton, they can steer so they can regain the work ability. So our project partner, Wang, is designing such exoskeleton. But the name is not the leg weight, the name is minor worker. I don't know why. And to test such things, we first have some stance by one leg, and we have so only the control objective is very simple. So just control the position of the central mass above the ankle, and also the support leg should be straight. And the human is perturbed at the trunk, and the leg in the air is just moving on its purpose to maintain such objective, while we don't specify any trajectories. So I will end up this method, the test, with a demo to use the trunk, control, or perturb the bipedal walking. So how does it work is we use trunk to control the robot, and so this the trunk motion can be a perturbation to the walking, and it can also be a control command to the walking. So if you bend 45 degrees, which means we trigger the start motion, then the robot will start to walk. And then the rest is self-explainable, and I think now it's time for questions.
Are there any questions? Yeah.
So a lot of spinal cord injury patients don't have control of their trunk far enough down to be able to lean like that. Have you looked at what happens when you only have, like, from here up with the torso and you're having to do this kind of into your shoulders and walk? Or are you just assuming full back control at the moment?
So at the moment, we select a patient which has a little bit lower injury at the spinal cord, so which they have a trunk motion.
Okay.
And yeah, for this upper, if their trunk is not functioning, then maybe for the next stage we can design a better exoskeleton.
Are you using the same model for your forward simulation prediction and your model predictive control, as well as the actual simulation that you're running? Or is there any modeling difference there?
So the model is more or less the same for the simulation, but the contact model are different. So for the actual model, the actual simulation in the model, they have a bit more complex context model. But for the forward model, because this net has to be in a real time, and we sacrifice the accuracy to have some really simple contact model, and yeah, so they are a bit different.
I would like to, Ludovic Rigetti, to set up the presentation, and we have time for one more question.
Would you talk in a bit more detail about the simple contact model?
The simple contact model is just a spring and a damping model.
Does that answer your question? Very good. If there are no more questions, then let's thank again for the presentation.